we are going to study some of the most important applications of CNNs to images and videos. The whole section is based on the paper Recent Advances in CNN, published in 2015. Don't hesitate to look at this paper for more information. As we have seen so far, the most important application of CNN is image classification. To classify images, you can just use any CNN we've seen before, but you can also design more complex architectures. For example, you can use a hierarchy of classifiers. In the first paper, the author proposed a training method that grows a network not only incrementally, but also hierarchically. In this method, classes are grouped according to similarities and are self-organized in two different levels. Following the same idea, the second paper introduces a method called deep CNNs by embedding deep CNNs into a category hierarchy. As before, the aim is to separate the classes that are very different from each other and then focus on the more complicated task of separating the classes that are close to each other. In this paper of 2018, the author follows the same ideas and builds a CNN to learn fine-grained features for subcategory recognition. They train a CNN and they look at the confusion matrix output by the algorithm. Based on this confusion matrix, they automatically identify the classes that are confounded with each other and automatically create subgroups of classes such that the algorithm differentiates easily between the two classes in two different subgroups. However, it may be difficult for the algorithm to predict precisely in which class the observation belongs. Then you can train one specific CNN for each subgroups in order to differentiate the classes inside each group. The resulting classifier may be more precise than training one single classifier on the whole dataset. This heuristic is based on the divide and conquer paradigm. You automatically separate the problem into several smaller problems in which data are similar to each other and which may be simpler to solve. Here are the predictions given by AlexNet. Pictures are on the left and the configured set on the right displays the images confounded with the first image. Visually, it seems really complicated to tell the difference between all categories that are confounded with each other. Now that we have run AlexNet and identified the classes that are confounded with each other, we can create the subgroups mentioned before and train classifiers on each subgroup. Let's look at the first table. Each column corresponds to different architectures for AlexNet. On the left, you see that you have different basic models where T0 corresponds to a single AlexNet, T1 corresponds to an architecture composed of a first AlexNet and then other AlexNets trained on each automatically created subgroups. This is a tree structure with a depth of 1. Similarly, T2 corresponds to a tree architecture of depth 2. Each prediction results from 3 consecutive AlexNets. The percentage of error is displayed and shows improvements between T0 and T1. A tree architecture of depth 1, 2 layers of AlexNet, seems to improve the prediction of a single AlexNet. Bigger trees seem not relevant to improve the accuracy. The same results hold for GoogleNet as shown by the second table.